Hi folks, so the questions we have in front of us here today, guys, are from the 2017 Leaving Cert Higher Level Section A paper. What you have to do is you have 4 questions on the page as always, and you have to do 3. Okay, so what we're going to do in this video today is we're going to work through them from A1 to A2, A3 to A4, okay, and we'll just go through the kind of points explaining on each one. Alright, so we're going to start off here with A1, so I'll just zoom out to that one there now. So in this question for A1, it says the image below shows a Bluetooth mini speaker. The speaker is based on a cube with its faces cut as shown. So you can see here we kind of have the little mini speaker, and you can see kind of lines cutting through it, okay, cutting the faces up into these kind of fairly irregular shapes. It says the drawing on the right shows an incomplete axonometric projection of a similar cube using the axonometric axes method. The planes of reference are also included. The elevation and plan are shown in their required positions with lines drawn on the 3 visible faces. So it says part A, complete the axonometric projection of the cube and the given lines, and part B, determine the true angle between the lines AB and CD. Okay, so you can see here, guys, they've given us the plan view of the cube here. This is elevation of it here. And what they're doing here in the section here where the axonometric is they're trying to complete the 3D view of it, the axonometric view on the axonometric plane. So this is a case of being able to understand, obviously, going from 2D into 3D. So I assume when they say it's axonometric and it is an isometric, yeah, our planes of reference are all, just checking there, yeah, 30 degrees, okay. So this is an isometric version of the axonometric plane, okay, where we're going to bring back our lines at 30 degrees, okay. So looking at this now, you can see they've already got this face here, okay. This face here is very, very important to us, and we can see that face is dictated down here in our plan view. We see that face as an edge view, okay. That face there is an edge view, whereas up in this one here we can kind of see an angled view of it. So what we have to do is we have to locate, obviously they've given us the line CD. You can see the lines were brought back, okay. So if I was to project C back, I assume they have it in the correct position, but just to prove it, I would project it back like that. And that would show us where C is, okay. Nice and easy. Likewise with D as well, and you can see they brought that back. Now, B is on the bottom surface, so I can bring that back straight away. And locate that down there. And likewise with A, that's on the top. So there's my A. And just going to put those in. So there is A. Write it there the best I can. And B. Okay, so we've kind of got that face completed there. Now what we have to do is we obviously have to complete the rest of the structure. So starting off, I'm actually just going to project up my points a little bit further. And projecting this guy back here. That's that back edge which is over here. That'll actually show me then where I can connect this to here, finally over here. That's just a case then of having that line in there. Okay, so we have the faces complete. Now what I have to do, you can see here clearly, I've also got this line here to complete on this face. So you've got 2 lines here. So one starts at D. I can see where it finishes. So project that across. Okay. And likewise with this point here, see it goes through, so it's a case of extending on, and the same with the top one. So I have that, and just connect those up. So this one connects up to here, happy with that, and then this guy over here which hits this edge connects across to D. So there we have it, we've got them 2 in. Now what we have to do is, if you look at the top surface as well, based off of our plan view here, we've also actually got 3 lines, okay? And I'm not sure, but I assume this one might be connected up to A. So it's just a case of finding those points on that surface. So project up all the points. Now this edge here will be seen as this edge. This one does look like it's connected to A. You can see there they're connected. So I'm happy with that. I'll project this one up further. I'm going to mark it there. Okay, don't have to bring the line up, just so I'm just going to be able to keep it neat and tidy, just to be able to guide it. Got two over here on this opposite edge on the far side. Okay, so starting with this one, going across here, we can see it's the inside one, so that's going to connect over to there. That's that one done. This guy here, just to be sure, I assume that was meant to connect up to that one. So based off of my, it was probably meant to be right here. So just make sure, so it's going to go to this guy. Happy with that. And then I have one more going from here over to here. Okay, just been able to follow yourself around it, okay, and you can see here we kind of have the little triangle structure inside it, and we've got that again, okay. So that there is part A completed, so I can tick that off. Now, part B, determine the true angle between the lines AB and CD. Okay, anytime you want to see the true angle between something, you're always going to have to be able to look straight at it, okay. So I want to see the true angle, between the lines AB and CD. So the only way to possibly do that is technically if I was a little guy and I was just literally standing right here. Okay, just drawing in a little stick figure there. Terrible stick figure, but you get the idea. And I was looking straight at that there. Okay, that is the only way I'll be able to tell the difference between the angle between the lines. Now, the only way we can actually do that is by finding that face as an edge view. And in what view do I see that face as an edge view? I don't see it here, but if you come down here to our plan, I can see that face there, okay, with the lines A, B and CD, which will be on this face as an edge view. So if I look perpendicular to that, I will be able to see the true angle between those lines. So what I'm actually going to have to do here now is set up an X1, Y1, or an auxiliary view. So, parallel, bit of sliding set squares here. I'm going to set up an X1, Y1 parallel to the face. Let me load here a little bit further. Like that. And then projecting out my points perpendicular to it. So, that's going to be the width of the face. And I want to project out my points. Okay, I know C and D, okay, are on the edges, but A and B are not. So I know A is right here. It's going to be somewhere up there. And to actually find B, I'm going to actually have to locate that in my plan view, because I do have it here. So it's simply a case of projecting that down. And that's where B is going to be. Okay, so we'll actually write these in as well. So I know C is here. I know D is there, and this one is B, and this is A. Always use labels to guide you. Now, as I did with A, and all the other lines and points, project out B parallel to that as well. Okay, so there we have our auxiliary view set up. Just going to write in X1, Y1 there. Now what we have to do is project from the plan, you take your heights from your elevation. Okay, so this isn't actually too hard here. Straight away I know that the bottom edge is here, but I know the overall height of my object is this height right here. Take that height there, which will be the same as this height here. So I could mark that on any one of these lines going up. Mark it here. It would make sense just to mark it on the opposite side. Okay, project the line across. Another way I could have done that was I could have just marked it there and then done sliding set squares, which is actually what I'm going to do. Just keep everything in sync. They should be the same height, and as you can see they are. So there is our face when we look straight at it, which we can see is representing to us a square. Now it's about locating those points. Now the easiest one to locate is B, because B is on the ground. So I can find B here. I'm going to call it B1. And the next one I want to find is A. Okay, so I'll actually just take the perpendicular distance, and just to be fully accurate, I want to do my line up like this, just to get the exact height. I want that perpendicular height there, so I just wanted to make sure that I was getting the exact height. There's A. Okay, don't even know why I did that, just realised, sure, A has to be up here because it's on the top surface. A little bit of a brain fart there. So as B is on the bottom, A is on the top. I already have the top. Now it's a case then I have to get C and D. So to locate D, mark up the perpendicular height straight from the plan, take the heights from the elevation. So there's D. Find D in your plan, come out here to your X and Y1. There's D. Likewise with C. There's C. So C1, D1, and we're almost done the question now. C connects to D, A connects to B. The question said determine the true angles, determine the true angle between the lines A, B and CD. We can see the true angles between them. Okay, there we have it. There we have it. Okay, nice and easy. A, B, C, D. So the true angles, I suppose, A, B, C, D, a bit like that. Okay, you could measure it if you wanted. That angle would be the same as that angle. This angle will be the same as this angle. There's the true angles. Okay, found nice and easy. So that there, guys, is question A1 based on the axonometric projection topic, and obviously a little bit then on the orthographic, your orthographic understanding, and a bit on auxiliaries. So what we're going to do now is move down to question A2, which is based on the topic of conics. Okay. So question A2, it says the graphic below shows the logo for the Ladies Professional Golf Association. So we can see the logo down here. It contains a combination of geometric curves depicting a female golfer. The main curve is a parabola and the club shaft is a normal to the parabola. So I assume the main curve they're on about here is this red one, okay, which is a parabolic curve. And what they're saying then is that the club that the female golfer is holding, okay, is actually a normal, okay, to the parabola. So it says the drawing on the right shows the axis AA1 and the directrix DD1 and the focus of a similar parabola. So we have the directrix, which is going here, and we have the axis, and on the axis, which is AA1, we also have a focal point. So part A, locate the vertex and draw a portion of the parabola, and then part B, locate a point P on the curve, which is 30 millimeters from the directrix, and construct a normal to the curve at point P. So obviously we're going to have to get that kind of club shaft. So we're going to have to get the parabola first and then the shaft like that, okay, the club. So starting off, guys, with our conics, okay. The good thing about a parabola is nice. It's probably one of the easiest ones to do in this kind of topic. First of all, we have to locate our line of eccentricity, and for a parabola, okay, everything is equal, okay, parabola, okay, so from where our axis intersects our directrix, which is right here, we are going to project the line at 45 degrees, okay. That is our line of eccentricity, okay. So I'm just going to write in LOE. That is line of eccentricity. Now, what we have to do is we have to locate the vertex. The vertex is found by projecting from the focus at 45 degrees to hit the line of eccentricity. Where it hits the line of eccentricity, project it down perpendicular to your axis. So that there will give us the vertex. Just put in that little symbol there, perpendicular. That is our vertex. So we found our vertex. Now at this point, what I'm actually going to do is put in my focal line. So the line going up like that. Okay. And at this point, what we're going to do is follow the method for locating points on our parabolic curve. So first of all, probably the easiest one to find is right here. Usually on the focus, where the focus line meets the line of eccentricity will give you a point on the curve. The vertex itself is also a point on the curve. And what we have to do is we have to locate a series of more points, obviously above and below. But once you have them up on top, you can just do axial symmetry to find them below. So I'm just going to do some various, I suppose, cut lines here, and to help me find the points on the curve. So I'm going to pick a point there. I'm going to do a line up and down. I'm also going to do another one here. Do one in here, and one more. That'll probably be enough actually. I might do one more in a minute if I need to. Where every one of those lines that I just brought up and down, where every one of them hits my line of eccentricity, right here, I'm going to project it across to my focal line, here, here, and then where it hits it on this side, just project it the other way, and here. So I've done a series of them there. I've done 3 of them. Now to locate points on the parabolic curve, what I'm going to do is I'm going to put my compass point on my focus, and I'm going to go up here to the top one, to where this line projected across. I'm going to swing an arc like that. That there will locate a point on my parabolic curve. Where it is up here on the top half, I can also locate it on the bottom half. So same method. Where I projected that line across onto my focal line, swing an arc, find it below. Obviously we have a point here already, so I can actually take that distance, axial symmetry, mark it off on the opposite side, and then to find it on the inside, you can see obviously where we projected across here. And likewise here. So there's actually quite a distance between that point and the vertex. So I will take one more right in the middle, project it up and down as well a little bit further, and where it hits there, project across, and from my focus that will give me a point on the curve there and there. So there we have it. Just mark those. I like to usually just do a little dot. Obviously on the day you'd be using a pencil. It's probably a little bit neater than using these fairly blunt biros. I just think they come up better on the camera. Here as well, there's another one, another one, and another one. So quickly sketch that in. Okay, so there we have our parabolic curve. So that's the part A done. Part B, it says locate a point P on the curve which is 30 millimeters from the directrix and construct a normal to the curve at point P. So if I just come over here to our graphic, obviously we have the parabola. Basically what we're trying to find is this point right here, point P, and we want to find obviously our normal, which is perpendicular to any tangent that we could possibly get. So there's a few ways you could go about this. First of all, we're going to locate it, we're going to locate point P. So it's 30 millimeters from the directrix. So from the directrix, I'm just going to measure 30 millimeters back. Okay, so I can do it like this. 30 millimeters back along my axis line there. Where that is there, I'm going to mark up right there. And at that point there, I've now located point P. Okay. Now there is a couple of ways you could go about this. I could start off by getting a I suppose I could get a tangent. So I could connect point P, okay, and this is some common terminology and some common, how would I put it, methods to actually find a tangent, to be it a parabola, a hyperbola, or an ellipse. So where I connect the point, where the tangent, or in this case the normal, is going to be on the parabolic curve, if I connect that to my focus, perpendicular to that line, okay, so what I usually do is I put the long edge of the 45-degree set square on the line, so I'm going to put that perpendicular to that line, okay, and what I do then is with the other set square I put behind it, rotate it sideways, just like that, and from the focus do a line there, like that, to hit the directrix. And what you notice is, as I said, it's perpendicular, so just put in that little symbol there. So there's our perpendicular symbol, okay, so from the point to the focus, okay, and perpendicular to that, where that hits the directrix, okay, if I was to connect that up, and put this in very lightly here, through my point, what I've actually found there, with that line, is a tangent. And because I've found a tangent, we know that a normal is perpendicular to a tangent. That is a tangent through point P. So it's very easy here. I could also then rotate, and now I have my normal. Okay, so that's one way we could have done it. So once again, perpendicular like that. I won't put in the symbol this time, but basically that normal is perpendicular to my tangent line that I got. And I got the tangent by going from P to the focus, perpendicular to that line to hit the directrix. Where it hits the directrix, join through P, you get your tangent. Perpendicular tangent, you get your normal. Okay, so that's probably the way that I'd most often recognise with this kind of problem. Another way you could do it is, there's actually a quicker way. There's something that for some reason just never jumps in my head at the start. By connecting the points to the focus, I could also go perpendicular through the point from the directrix, so perpendicular to the directrix through the point. Okay, and what I've there now created is an angle. Okay, that angle created there, if I was to bisect that angle inside there, okay, between the perpendicular line from the directrix through point P and from point P to the focus, so that line there and this line, by bisecting that line, it's actually probably a bit easier than what I did, but I'm just showing you both ways. By bisecting that angle in there, I would also get the normal. Okay, but I do, just for the demonstration purposes of this video, it's always handy to understand how to get the tangent as well, and then obviously perpendicular to tangent gives you normal, but both ways would have sufficed in this question. Okay, so hope you found that helpful, guys. Now what we're going to do is we're going to move on to A3 at the top right of the page. Alright. So this question A3 here, guys, it says a design for a patio fireplace based on a regular solid is shown. Okay, so you can see here they've kind of given us a 3D graphic and they've kind of told us what it's based off of. The drawing shows the elevation and plan of a similar solid, and all faces are regular pentagons. Okay, so regular pentagons, okay, every side. If you look even here at the plan view, okay, the top surface here, you can see the pentagon. Every side is the same length, therefore all the internal and the exterior angles are the same as well. 72 degrees, 108 degrees in the interior angles. Part A. Using the given x1, y1, okay, so we're given an x1, y1, draw the true length of the line of intersection between the faces A and B, and hence determine the dihedral angle between those two faces. Okay, so they like these questions at times, guys, alright? They'll always ask you at some point in the leave insert in higher level to find the dihedral angle between two surfaces. Okay, so we have to first of all locate both surface A and B. So you can see here in my elevation I've got surface A here, okay, and I've also got surface B, and essentially what they're asking us is the dihedral angle between them surfaces. So we have to find the line of intersection, and we can see where A and B connect right here is this line. Okay, so that's our line of intersection, and technically what they're asking us is to kind of look down in there along the line of intersection until we see it as a point view, so we can actually determine that angle inside there. Okay, you will not see it in this view. Okay, so that angle in there is not the dihedral angle. You need to see the edge, the line of intersection, as a point view. So that's probably why they're asking us to get first of all the true length, where they say draw the true length of the line of intersection. So we have to get the true length of that line there. So first of all, we want to identify it. They've already given us the x1, y1, so let's locate that true length line, or sorry, that line of intersection in our plan view. And that line there in our plan view is actually this line here. Okay, very, very important. So that line right there is this line here. Therefore, making this surface in here, if I was just to kind of highlight it there, that surface in there is my surface A. This here is my surface B. Okay, so I'm just going to put that in there, B and A. And what I want to do is find the true length of that line. So this isn't too bad. The good thing about this is that my line is set up already, and I can project out to find the true length of that line. So just projecting out perpendicular to the x1, y1. And what's helpful there is straight away this point here, which is on the ground. So that's that point right there. And I also have to find the height, okay, of this point, which I can take, project from the plan, take your heights from the elevation, like that, perpendicular height there. Okay, just make sure I'm exactly on it. Yeah, happy with that. Come down to where the point is in my plan view, come out to the x and y1, mark it out. So there we have it. There we have the true length of our line of intersection. Okay, and then we have to work on to the second part of part A here, and hence determine the dihedral angle between the two faces. Okay, so what we actually need now is some points that are relevant on both faces. So just looking here and trying to see what I can do. I've got the true length of the line of intersection. I now need a point on surface A and surface B. And that's actually not bad, because I'd imagine, yep, okay, so what I'm actually going to do is, just to show you here by putting it in lightly, I'm going to connect that to that. I'm also going to connect this point down here, that. And essentially what I have is, I have these 2 points here. Okay, I have this one and I have this one, okay, which helps get us the line of intersection as a true length. Now I need a point on surface A and a point on surface B to be able to determine the dihedral angle. So what I've done here is I've kind of created 2 triangular surfaces. Okay, I've created a triangular surface on A, and I've also created a triangular surface on B, but they both include the line of intersection, so that's very important. And what's helpful about these ones is that both A and B are in line with each other, so what I can do is I can project them across. Okay, and what's helpful there, didn't have to bring it out that far, but I know that both this point here and this point here, it's the pentagon on the bottom as it rests on the bottom, therefore that point is right there. Okay, so I know technically they both connect up like that. Okay, so I'm not going to give them labels now, but that point there is here, and also B is right here, and they both connect up there like that. Okay, so what I want to do now is I want to look out along my true length. Okay, so I'm going to look out, I'm going to set up an x2, y2 perpendicular to my true length. Okay, because that's the true length, and I want to see that true length as a point view. So it's like taking a line and we've twisted it around. That's the true length of my pen there as it sits on the table, and I want to twist it around until I see it as a point. Okay, and when I see it as a point, then I'll be able to actually tell where this point is, and get the dihedral angle between those surfaces. So in doing that, I'm going to set up perpendicular this is actually called an x2, y2, so perpendicular, and I need to now project out like that, then like this. Okay, and what we do now is when we take an x2, y2, we take the distances from the previous xy line back. So the first distance I'm going to take is from my true length line, and I can see here from this point here back to here is the same as from this 1, which is the xy line, x1, y1 back to here, so it's the same distance, thereby giving me a point view of my line of intersection. So I take that distance right there, I come out to here, mark it out. So as you can see there, I just need to extend my line out a little bit further. Okay, so right there, that's my right in point view, LOI, line of intersection, point view, LOI. Now what I want to do is I want to mark the distance back to the point that was on surface A, which was that distance there, and going to come out to where the point was here, follow it out to my x2, y2, mark that out. Now I'm going to mark the distance from my x1, y1 out to surface B, or the point that I was looking for on surface B, I should say. It's right here. Same thing, that's where it was. Find it out here on my x1, y1. And that's there on the one to surface A. This is the one on the surface B. Connect them both to your point view of the line of intersection, thereby determining the dihedral angle between surface B, which I'm now seeing as an edge view, and surface A, which I also see as an edge view. The angle in there is my dihedral angle. Okay, so that's the part A done there, guys. Just a little bit of understanding, okay, but this will always be thrown at you at some point in the Leaving Cert DCG test. Now, part B, it says determine the center point of face B. Okay, so face B is down here, it's up here in our elevation. In plan and draw the projections of a sphere which rests on the horizontal plane and is also in tangential contact with the center point of face B. Okay, they're actually bringing in a little bit of solids in contact here. So first of all, we have to find the center point of surface B. Okay, so let me just think about that there now. So what we want to do is we want to basically get the center of one of these pentagonal faces, okay, these regular pentagonal faces. Now, our surface B, as we can see, guys, is in here. And the issue we have with that is, obviously, that is not the true shape of surface B. Obviously, we know the true shape of it is here, okay. So if I just take this one that is here, okay, in the plan view, I know it's not the correct one that we're using, but just for demonstration purposes and explanation, how would I find the center of that? So there's a couple of ways. What you could do is you could bisect the angle, okay, the interior angle, okay, bisect that, that'll go through the middle. I could also bisect this interior angle, and where the two of those bisectors meet, that'll give me the center. Another way I could do it is also by, instead of bisecting the angles, okay, I could also bisect the lines, okay, and that's probably the easiest one for me here, because if I bisected this line, what's important to note is if I was to bisect this line, I know the middle of it would be there, but the middle actually would line up directly with this point up here. Likewise, if I bisected this line, the middle of it would line up directly with this point opposite here. So that's probably the one I'm going to go with, okay. And the reason for that is because on my surface B, okay, I have one of those kind of 5 edges is actually a true length, and this one here, okay, is very, very helpful to us because that one there is actually sitting on the ground, okay. It's technically this line here, okay, that's sitting on the ground, and because that's sitting on the ground in my plan view, that is a true length. And I can see already that technically has been bisected for us because it connects up to the top there. So somewhere along that line there is actually the center point of my face B. Now, the only other face or the only other edge on surface B that I do have as a true length is right here. Okay, and technically what I could do is I could bisect that here, get the middle of it here, project it back, or I could just bisect it right here as well. That technically will work as well. Okay, and I would actually, once I get the middle of this line here, I'll connect it to the point opposite. Remember, like I did up here or here, I can connect it to the point opposite. So for the sake of this, I'm actually going to just clean that up a little bit. I'm actually going to bisect this line. Do you know what? I'll bisect this one. It's just straight. So put my compass point there. compass point here, and having bisected that, okay, I can now extend that point on the opposite side, and what I've actually found that is really helpful to me now is the center point here. Okay, so what we have is determine the center point of face B. Perfect, we've got the center point now of face B. And now what we want to do is we want to draw the projections of a sphere which rests on the horizontal plane. Okay, so it's sitting on the XY line, which is helpful to us, and is also tangential to the center point of face B. So what I actually need to do for this one is I actually need to see face B as an edge view. So the only way I can see it as an edge view is to be able to look along one of those edges, okay, that are on the surface. Okay, so this one is actually going to be helpful to me again because that is sitting on the ground. So if I look along that and see it as a point view, I can then see the surface as an edge view. So I'm going to set up an x1, y1 perpendicular to that. Once again, hopefully this should work out here. I probably went too long with that now. So it's another x1, y1. Okay. So that point right there, I'll project that up here. That will be on the ground. These 2 points will be at the same height. Then I've got this one be up here. Okay, and what we're going to do is going to take the perpendicular heights. So I know the height, these 2 points here on the ground, so technically this point and this point right here. Okay, that's my point view of the edge because that's a true length. I'm going to take the perpendicular height for this guy, which is the same as the height for this guy, which is these ones here. So follow them up. Okay, at that point there I technically have my edge, but just to be able to make sure I'm fully accurate, okay, this is where a video could go wrong. Just want to check that perpendicular height there is one I'm taking next for the topmost point on the surface, right there, and that topmost point is here in my plan. Mark it up. And if I am accurate, those 3 points should meet in a line, and we'll see, do they? Yes, they do. Happy with that. So there is an edge view of my surface. Okay, so technically there's 2 points here. These 2 points, which is this one and this one, are here, and then the top point, which is this one. And what we have is we have an edge view of the surface, and we know that it's in contact with point B, which is in the center of it. So I can actually project that up as well now. So open the sliding set squares once again. So find the center point of the face. It's just a case of projecting it up. Okay, so right there is my center point, and we know that a circle, going back to our solids in contact, okay, that when it's touching the face, or any face or extreme generator and the horizontal plane, what we're going to do is we're just going to bisect the angle between the edge view here and the XY line, or the x1, y1 in this case. So I'm going to bisect this angle in here. And somewhere out along that bisector is a circle, or a sphere, sorry, I should say, that is equidistant from both the XY line, or x1, y1, and our edge view. So, using the center points that we have, which is right here, I'm going to now project out perpendicular to my edge view. There's a bit of work in this one. Perpendicular there. And having projected out perpendicular, put that in there like that, I have actually found my center point. And Please bear with me now, because using biros is not always the most easy. So I'm trying to draw in my sphere if I possibly can. Hopefully it works out for me. It might go a little bit below the line. We'll see. Not too bad. So there's our sphere with our radius, as we can see. Now what I'll have to do is project those back. So I've got the center point now. The center point is right here. So it's actually going to be quite helpful in my plan view. It's simply a case of take the exact same radius, mark down here. The center has to be out straight, perpendicular from B, which we have it. What happens is right there. It is actually going to go in as, I should say, hidden detail. Put it in as this point here on the outside. That's all heavy. So there's my plan of it. Just to put it in a little bit better there. And the last part then is, if I find it in my plan, I need to also find it in my elevation. Seems to work out perfect. Mark up the exact same height, radius. So my center is right there, and draw it in. And this position now, I will see it fully heavy. And then it's a case of using a pen here to heavy in the last edge. I can see now why I left this not fully heavied in. Okay, so what we have is that edge there heavied in, and then a little bit of hidden detail inside here. So quite a bit in that one there, going from the dihedral angle to a bit of solids in contact, where we had to take an auxiliary, another auxiliary, and then an auxiliary here to get edge views, point views, edge views, true lengths. Okay, so quite a good bit of understanding in that one. So what we're going to do now, guys, is move on to the final problem here at the bottom of the page, question A4. Okay. So the last question here, guys, it says A4, the plan, elevation and end view of an archery target are shown. So we can actually see, so the target is here, okay, so we've got the elevation here, we've got the plan view here, which would nearly be seen as an ellipse, okay, and then the end elevation we're seeing it as an edge, okay. The line PA represents the plan of an arrow, so we can see the plan view of an arrow, okay, just before it hits the target. The arrow travels horizontally in a straight flight path. Okay, so just thinking about that. Alright, part A, draw the arrow PA in the end view and in the elevation. Okay, so we'll tackle part A first before we get on to part B and part C. So the line PA represents the plan of an arrow, so we've got the plan of it, okay, and we've got point P in our end elevation, and we should be able to find, okay, so straight away I'm actually going to find point P in my elevation, so straight across, and I know that P is here, so this technique right here is P in my elevation right there, okay, and it says draw the arrow PA in end view and elevation, okay, so this isn't actually too hard. So for my end view, I'm going to project that across to here. For my elevation, I know it's going to be, work out the height of it in a minute. It's actually the same height, what am I saying? Up there. I'll tell you why it's the same height as P in a second. So, using my compass, I'm going to rotate A in my plan, okay, where it hits here, my XY line, project it up, And what's helpful there is, and I'll tell you why I knew it was the same height, it said the line PA represents the plan of an arrow just before it hits the target. The arrow travels horizontally. So that's the most helpful part there. The arrow travels horizontally. So I know the arrow is travelling horizontal like that. It's not angled or anything like that in relation to the horizontal plane. It's travelled horizontally in a straight flight path. So that's what was helpful there. So I know the arrow then is here. So there technically is my A. And so I know A is at the same height. So because A is at the same height, I can bring that across. There is my A in elevation. So there's the arrow as it would appear in elevation. And obviously generally you would have the head there like that, and obviously the tail of the arrow. Okay? But we're just seeing as they're talking about a line here, which is representing the arrow. So part A, done. Not too bad. Part B. Determine the projections of the arrow when it hits the target. Okay. The arrow is travelling obviously in a straight line path, so it's going to be here. I'd imagine then from here it's going to move over here somewhere. What we want to do is we want to determine where it hits the target. Okay, so we have the actual length of the arrow here. Okay, we have kind of the rough length of it here. This is the only view that I can actually see it as a true length. So first of all, the arrow is actually going to continue in this direction, because in my plan view I've kind of got the angle that it makes in relation to the vertical plane, which is the XY line. So it's going to go in that direction there somewhere. I assume it's going to hit somewhere in around here. And I can actually find the exact position of that, because in this view I've got my target as an edge. So we can see the arrow is travelling there, travelling, hits it right here. Where it hits it here, okay, I can project that down to my plan. So this is still simply just understanding how it's read. Okay, once again, keep taking this out, travel that around. So I found it here. I want to find the exact position of it. Okay, that is the exact point of where it enters my target, right there. Okay, and as I said in my plan view, okay, I've got three lines PA in elevation, end elevation, and my plan. This is the only one that is actually a true length of the arrow. Okay, because in this one we're looking directly down it, and because we know it is parallel with the XY line in elevation, it makes it a true length of my plan. So I'm actually going to take that distance. Okay, take the distance for PA on my compass, and I'm going to mark it out from where it hit the target backwards. Okay, so essentially PA has travelled to here, P has travelled to here, so just the new position of my line PA. That's all that I've done here essentially. Okay, and if I found that new line PA in my plan, I suppose I'll have to find it in my elevation as well, and my end elevation. So my elevation is actually easy enough thing to do. Project it up, project it up, and project it across. So that's my arrow as it is entered. At this point it enters the actual target, and that's the tail of the arrow. So obviously once again that's P, that's A, and I have to represent that over here. So rotating back around, okay, and projecting up, and once again just drawing that in. Okay, so there we have part B done. That one wasn't actually too bad either, pretty similar. It was just a case of understanding where the actual entrance point was. Now the last part, it says a second arrow travelling in a straight line. Okay, so once again travelling in a straight line also passes through point P. So we have another arrow that is passing through point P in a straight line, okay, and hits the target at the bullseye. Okay, so we have another arrow that is obviously travelling, and this one they've obviously managed to shoot a little bit better than the last one. It's gone through point P again and it's hit the bullseye. Okay, so that's important there to note. It does make entrance right there. Okay, also obviously makes entrance right here, and wherever that would be, I assume in this view would be here. Okay, so we can actually see the difference now. It's actually a little bit lower. Okay, I should read the rest of the question. And then it says determine the true angle between the two flight paths. Right, I'm just thinking two flight paths, two lines, planes. Okay, yeah, alright. Just trying to work this out in my head, guys, sorry. So I'm going to read it again. A second arrow travelling in a straight line also passes through point P and hits the target at the bullseye, which is the center point. Okay, have we got the center point in our end elevation? Yes, right here. Okay, and determine the true angle between the two flight paths. I just want to highlight that bit just for myself. I find sometimes if I just highlight that rather than going back having to search for it, it's helpful. So I want to determine the true angle between the two flight paths. So essentially I need to see whatever it is, the angle between them straight on. Okay, so I might have to take an auxiliary or a rebatment. Okay, rebatment. Okay, so a second arrow travelling in a straight line also passes through point P. So it goes through point P and it hits the center point, which is the bullseye. Okay, so can I make that line? Yes, I can. I can actually draw that in my plan. I'm just going to put that in heavy now. Well, I say heavy, I'm going to put it in a little bit. So that's the flight path right there. Okay, can I represent that in my end elevation? I actually can, because it says it goes through point P and it hits. Okay, this is becoming a little bit clearer now. Sometimes it's just a case of talking it through and working the way through the problem. So the first arrow, PA, it said it travelled horizontally with the XY line. Okay, this one has hit the bullseye, but it's obviously, we can see it's gone in straight kind of at an angle. Okay, and in this view how it would appear is going like this, I suppose. Okay, and essentially just looking at that there now, so PA, look at that there. I'm going to create a plane like that. Yep, essentially what they're asking us is to determine the angle between the flight path of arrow PA and the flight path of arrow, in this case I'm just going to call it PB. Put that as A there, PA. Now see, this is PA, probably should have labelled it. Okay, PA. Okay, so that's where PA was. Okay, and this is PB. I'm just calling it PB because it hits the bullseye. And technically they're asking us for the true angle between them. Now that is not the true angle there, and the reason for that is because even though this line here is parallel with the XY line, okay, PB isn't a true length. Okay, so we're not going to be able to get it there. The one we might be able to get it to, I think, is actually going to be down here. So I've got PB, okay, which is here, and I've also got PA, which is here. Alright, I actually think I have it now. Yeah. Okay, working it out. So essentially, there's our plane. Okay, so if you look at that, if you think of this set square, okay, where the point here is point P, okay, the point here is point P, A is here, and B, where it hits the bullseye, is at this point. Okay, so that's essentially our kind of our 30-60 set square there. But what we want to do is we want to find the true angle. And as you can see, okay, when I twist it like this, okay, when it's flat down there, we know the angle of our set square is 30 degrees. The problem is, the minute I start to tilt it, even though in reality we know it's 30 degrees, the minute I start to tilt it up towards the camera there, even though in reality we know it's 30 degrees, that angle does not appear as 30 degrees anymore. Okay, it'll only appear as 30 degrees when I have it flat down on the surface. But when I tilt it up, we don't see it. You can actually see the angle there getting quite acute. Okay, this is maybe 10 degrees or something like that. And that's the problem we have here, because we know PB, okay, is down lower than PA. So technically what I'm trying to do is I'm trying to take it, where in this case, how would I put it, it's kind of like that, it's down low. I want to tilt it up where A is up here, B is down lower, okay, obviously P is off over here off the camera, but I want to tilt it up so that they're flat like that, okay. And in that view, when they're flat like that, as I look down on top of it in my plan view, which I'll see it down here, I'll be able to then determine the true angle. So what I can actually do to do that is, I'm just trying to find, is it a true length anywhere? PB. So just figuring that out, guys, we can actually determine that the line PB, I've just realized, okay, because I'm looking at the arrow here, or the flight path of the arrow PB, okay, because that arrow, okay, when I'm looking in this view with it, okay, I'm technically looking perpendicular to the arrow there, that actually makes that arrow here in this view a true length, or the path of it, I should say. So that line there from P to B is a true length, because as I said, it travelled through P straight and hit the bullseye. And in this view, the end view, technically it's like a person was standing here looking in the direction of my finger there. Therefore, because that's perpendicular to it, we see that line as a true length over here. Okay, so I can actually take that distance on my compass from P to B. It is quite hard. It takes a little bit of understanding of lines and true lengths and geometries. So I've taken that distance on my compass. Okay, I'm going to have that ready there. And what I'm actually going to do is I'm going to rabat it. So to rabat it, I'm going to take B, and it's like I'm flipping it over, and in my plan view, how that would appear is, I should have written B in there earlier, sorry as well. That's B right there. And what I'm doing is I'm flipping it over so that it's up parallel with A. And in my plan view, technically what's happening here is, although it appears just as a line, really this line is representing an arc, where B is actually coming up off the sheet, okay, and then going to come down flat down here, okay. And how I'll actually be able to determine the point out here is by taking the true length of PB and coming to P in my plan, marking it out there. Where that comes out there, I should put it in red. That line right there, just to show you, there's a difference between this one here. So I've got the new position of B here, let's call it B1. B has obviously rabatted up, come over here, and now it's at the same height. So it's basically like I took B and it's gone up here to this, and as we look down on top of it, then we can actually see the true angle. And the true angle between arrows PA and PB, or term the true angle between the two flight paths, is the angle inside here, okay, and whatever that is, okay. So that was a little bit tricky there now, guys. It actually stumped me there for a second, well, more than a second there. I had to have a little think about it. That there is the true angle, guys, between the flight paths of the arrow PA and PB, and it's just essentially about creating a plane up here and then rabatting that plane up in your plan view, okay. Hope you found that helpful, guys. That is the 4 questions from 2017 section A completed. Okay.